There we go. Cool. Well, let's go ahead. Thank you for joining this month's ESIP and USGS Community for Data Integration, Information Technology and Interoperability Rant and Rave. This webinar series was previously called the Tech Dives, which is still more or less what it is, but this year I've kind of brought us back to this idea of a rant and rave, which is to talk about the stuff that's great and exciting, but also to give people an opportunity to talk about some of the frustrations and tensions involved in interoperability and information technology. And so this month, Mike Johnson from Lynker, who's working as an affiliate of the Office of Water Prediction in the National Weather Service within NOAA, is joining us to talk about a couple of virtual dataset access patterns. This is an especially good talk for this group because it's simultaneously cloud, community IT tech, and Mike's done a lot of really cool work with USGS data. So the fact that this is a community and USGS group, this fits really well. So I guess I want to say Mike has done some of the most cutting edge work I've seen to date using the GDAL-based virtual dataset access techniques. And there's been a lot of traffic and a lot of talk about the X-ray ZAR kind of virtual dataset access patterns, but I don't think there's been as much socialization of some of these other access patterns that are very similar in concept, but different in their kind of accessibility and where they lie in the software ecosystem. So before we turn it to Mike, next month, Tom Krolitis from the kind of open source geospatial Python community is going to be joining us to do a rant and rave on kind of historical and current trends and drivers, I guess, of open source geospatial Python capabilities, and that should be really interesting. Tom's been around the community through the OGC Web Services XML days and now into the JSON OGC API days, and I'm really excited to hear him kind of hear his take on kind of where things are, where they've come from, and where they're going. So I hope you can join us next month for that. And with that, I'll remind everybody we are in a Google Doc, hopefully taking notes and capturing takeaways. And I'll turn it to Mike to take it from here.
Awesome. Yeah, thanks, Dave. And thanks for inviting me. It seems like a really cool group to get involved in more in the future ones. So as Dave said, I'm going to try to talk a little bit about some virtual access patterns and how we've used them to overcome a few challenges that we faced at NOAA OWP in terms of trying to build data sets and data access patterns to meet a lot of water modeling needs, but just general earth science in general. So topics for today, I want to try to cover three things that we'll rant and rave about in different contexts. One is the VRT format. This is GDAL's virtual format. They're VSI access patterns, which allow us to access files as if they're local, regardless of where they're distributed. And then at the end, maybe a little bit on flat data catalogs, if time allows, and how we've used some of these technologies to expedite data access and data federation for our group. The underlying context that I kind of want to talk about these in is the fair data idea. This is if data is findable, accessible, interoperable, and reusable. I'm sure this group's pretty familiar with it, but I'll keep coming back to how we're trying to use these virtual access patterns to make data a little more fair, regardless of where it is or how it's hosted. So my wife, she's a third grade teacher. She showed her class Inside Out yesterday. So when Dave talked about a rant and a rave, the anger and the joy came to mind because I think it really is kind of how I feel about working with some of this cloud data. So the rant number one would be publishing data online, even if it's cloud or web accessible, is not enough to simply make it fair. Sometimes it's not easy to find these data sets. The access patterns are different at times. And I wanted to point out a few data sets that we have had tremendous use from, but kind of fall a little bit short on some of these, even though they're almost there. They're like 2% off of being fair in the way we described above. So one of them would be LCMAP. They have these complex URLs that require manual generation based on semi-opaque dictionaries. So as long as you're able to build this URL based off of these kind of hard to understand sometimes acronyms and abbreviations. You can access data virtually, and we'll look at some of that towards the end when we get to this. But this would be one hurdle that kind of comes to using this data in a fair way. 3DEP is another one. I mean, almost everything we do in hydrology world requires DEMs of some sort. If you look at the national map, these are stored 1 degree tiles. You can see the north and easting based off how they're split up. These artificial boundaries that based on these tiles are meaningless in the sense of how we want to use the data. They make good sense about how they're tiled and distributed. But for our use, when we typically have use cases that might spread different tiles, even at times 2 or 3 or 4 different tiles, this access pattern can be a little difficult to find what data set we want exactly, which ones to download, which ones to use. Different times we use the Oak Ridge FIM data sets. This again is really nice data that's publicly accessible. It is online, but again, it has some hurdles in how we actually access it. They're huge data sets stored in by HUC6, which is a hydrologic unit. And some of them can be pretty big. For example, I took the first one in this HUC6 code and downloaded it this morning just to see. It was 8 gigabytes of data. It unzipped to about 13 gigs of data. And really all I wanted in it was one TIFF file. It was about 50 megs. So it's a lot of hurdle or burden, I guess, to get to data that you want simply by the distribution pattern that was chosen for this particular really useful data set. And then the last one is National Water Model Output. It's stored as netcdf files. So these other ones we've seen have been TIFF files of some sort. These also have somewhat of an opaque name. They change every 2 days. So you get new data every hour, and then they kind of die every 48 hours from this particular server and are moved over to AWS or Google Cloud Compute. So finding the data, finding the metadata attributes, finding the actual variables that are stored in all of these can be a real challenge. So those are 4 use cases that I kind of want to have in the back of our mind as we look at some of these virtual access patterns and how they've been useful for us in context of these data sets and many, many others. So the common issues, again, that general framing is often where is this data and how do you find it? Like if we weren't pointed to it by a USGS group, I wouldn't know necessarily where to find the LCMAP URLs. 3DEP is on national map, that's nice, but building out the particular file you want, that can be a bit challenging. So there's some challenges with definability, the access for these particular data sets. The interoperability is actually pretty good because they're using common standard formats. But in a lot of ways, based on how they're served, data duplication download isn't necessarily reuse per se. So we have kind of that tension with data reuse. So then getting into the Raves, one of the great way we can interact with this data is through GDAL's VRT files. When we talk about how these data sets are distributed in different units that make sense for their application, HUC6, 1 degree tiles, timestamps, we can start accessing these as aggregates using this GDAL virtual format. So the VRT is an XML-based format that comes within GDAL, and it allows many different data sets or single data sets to be accessed as aggregates. So if you create a VRT of a set of data, you can generally access them as a single individual entity. And so if we look at the very simple idea of what a VRT is, this is straight out of the GDAL documentation. If you have some TIFF file somewhere called UTM, the VRT is an XML form that tells you kind of the shape of the particular grid you're looking at. So this UTM has 512 rows, 512 columns, has some geotransform, it stores some sort of information, and it ultimately points to where the source data is. So relative to this VRT file that we have, there's a file called UTM-TIFF where the actual data is stored. So this is the most simplistic kind of VRT. It's pointing to one particular file, and it's not really changing the information itself. It's just describing it in this XML format. So when we want to talk about how VRTs can be used, let's take a use case that we want to get some elevation for the city of Fort Collins, but we don't necessarily want to compute what degree tile Fort Collins sits in and then go download that from the national map and then start accessing that tile once it's on our local disk. So the initial local VRT solution that we might try to use to demonstrate the power of this is we might download all of the desired data. We might download the entire collection of 3DEP, so every one of those 1 degree tiles. We're going to create a VRT file using GDAL based off all of that local data. And then we can access all of that local data, even though it's spread across many different files as a single entity. So the first step, which you can imagine probably takes a long time, would be we download the data. Once we have that, creating the VRT is actually pretty easy using the simple straight GDAL utility. So there's a GDAL build VRT. It's just a command that says we're going to build a VRT based off some input file list. The input file list we're going to give it is just a text file that has a bunch of paths. So again, in this example, we would have downloaded every NED tile, put them somewhere on our local disk. Here we're in our home directory under GitHub, whatever have you. And we're going to create some VRT file out of it. If we look at the VRT that would be produced from that, we can see that we now have an aggregated grid shape at the top. So when we saw that first VRT example, it was the same as the source data set because it was only accessing that individual file. But now we have an aggregated grid shape. It has its spatial reference system. It has a lot of rows. It has a lot of columns. And it points individually to a bunch of source files, right? So this is just the top of this file. It goes on and on and on, as you can imagine, for each of those 1 degree tiles. But within this ultimate aggregate set, we have each individual source data set and the sub-grid shape. And what this allows us to do is access this one individual file and pull data out for anywhere in the domain of that particular data set. So instead of looking at each individual 1 degree tile, we have an individual VRT file that spans the domain of CONUS rather than the 1 degree tile domain you would get with any of the individual TIFF files. And towards our use case then, so long as we have that local VRT, we can open it up, we can crop it to a particular area, in this case 4 columns, and all of a sudden we have our data. So we can see how that's a nice step forward, and we don't have to worry about finding which individual sub data set we want. The VRT allows us just to look at it all in aggregate. We return to some of our common issues, right? We're still dealing with some findability issues, right? This is on my local disk. This file is just mine. I can't share with other people, so there's still some challenges with that. But all of a sudden, the access pattern has become much simpler, right? You point to one file. It doesn't matter where you are, how big or small your domain is, you'll be able to extract data for the area that you want. The interoperability is actually really good now because you can point that VRT whatever programming language you want. You can use GDAL on the command line. You can use R, as we were doing in that last example. You can open it up with Fiona, Rio, and Python. You can take your pick. But again, we really didn't do so great with this data reuse because we had to download everything and keep it local. If one of those tiles updates on national map, we either have to figure out how to keep that up to date, or we're going to be using out of date information. And that kind of leads then to rant 2, and that data distribution and download is not de facto data reuse. I've seen a lot of groups. NOAA is a violator of this sometimes as well, that we want to download all the data, keep it local because we want to make sure we have it and it doesn't change. But in doing that, you're not engaging with the community or around that data set. You're just pulling it down and making it useful for yourself. So this then brings us to Rave number 2, which is the virtual system interfaces that GDAL has as well. So in the C parts of GDAL, right, there's these VSI descriptions. And if we look at the description of the C code, it says it's intended to allow virtualization of disk IO so that any non-file data can be made to appear as files. So that's pretty cool, but I don't know how to write C code. A lot of people don't. How do we actually use this? And it's nice that GDAL provides this information for us, or for this capabilities, in a few kind of pre-canned ways. So in general, GDAL accesses files on standard systems. This could be your Windows directory, your Mac directory, Unix system, whatever it might be. But it does this through the abstraction of individual kind of array files. By using these VSI commands, it makes it possible to access less standard types, such as the memory, the compressed files, encrypted files, data stored on different networks, private buckets, public buckets, different cloud systems, directly by changing the prefix of the path that you're looking at. So a few that we'll look at today are VSI S3. This allows you access to data in S3 buckets. VSI curl, this allows us access over HTTP or HTTPS, and VSI zip, which allows us to access zipped files. There's also VSI gzip, VSI tar, VSI S7 zip, depending on the zip nature of the file you're accessing. So in all of these cases, the prefix is kind of following this pattern that we have this VSI command with some prefix based off the type of data we're trying to access. So here again, VSI S3 is looking at an S3 bucket. It's using that S3 protocol to pull data down into that GDAL abstraction. So if we look at one of those degree tiles that sits in national map, right? I just pulled a random one. This happens to be the one between the north 6 and the east 163rd. You can pull that HTTPS URL of where that data lives. And simply by putting VSI curl on the front of it, because we're dealing with an HTTPS here, you can access that data as if it was local. So I no longer need to download this particular data set and access it directly through there. And we can see we're able to pull the information. Right now, we're just getting the metadata, the extent, the resolution. So you need to crop or pull that data down to actually use it locally, but we're establishing that connection in order to stream data. If we want to look at a VRT or a VSI solution to kind of overcome some of those issues we saw with the first one, we can bypass that need to download all the data locally. So instead of creating a VRT file of local file paths, we can create a VRT file based off the VSI prefix of the files we want to access. So in this case, on that first example, we made that long text file that had a bunch of, root directory, GitHub, wherever the data was living. Now we're going to create a list of files that say, this got bumped, I'm sorry. All these yellows should be shifted down just a bit. That the source files we want to look at are VSI curls of the URL where that base data sits. And if you're able to just kind of scrape those paths, append a VSI command to it, and pass that to GDAL build VRT, you then have a VRT file that acts off of the remote data. So you no longer need to download it, and we get all of those benefits we saw before, that these act as a single local entity. And the cool thing is that once you have that VRT file pointing to remote data, it doesn't really matter where you're using it from. So here, for example, we have this USGS Seamless 13 VRT. We can see again, it's sitting in a root directory. We can still access that data as a collective, right? So we have the entire domain of CONUS, all of the elevation data from a local file. USGS and the 3DEP program itself has actually hosted this VRT, so we can go straight to that national map bucket. Because it's HTTPS, we put VSI curl on there, and we see when we open up this particular path, we're getting the same information that we would locally. We also downloaded this path and threw it up in an S3 bucket that we maintain for NOAA. You can see by changing the VSI curl to VSI S3, we're getting the same information. And the cool thing with what's happening here is USGS updates those 1 degree tiles on a semi-regular basis. As long as the paths and files don't change, if those particular files update, anytime you connect to this VRT, you're going to get the updated 1 degree tiles as an aggregate of all of them. So you no longer have to keep them up to date. The data provenance and the data ownership is with USGS 3DEP where it belongs. But regardless of where you're accessing it from, you're going to get that latest and greatest in a single aggregated way. Just to go back to that use case then at the beginning, this happened to be the one that's on the national map server, right? Same thing we saw before, open up a connection, crop it to an AOI again being Fort Collins, pull down some elevation data. We actually have access to elevation data for Fort Collins. If you know the area, here's Poudre River, Horsetooth Reservoir in about 2 seconds. We didn't need to figure out where the 1 degree tiles that we fit in. We didn't have to figure out any sort of access pattern. We initially or immediately had access to the data we wanted in a time that works well. USGS went through and said, hey, we've got better LiDAR that flew over Fort Collins, and they updated the 1 degree tile that covered this area. We would never have to know. The data would just automatically update because those paths stay consistent. So if we return to our common issues using this VRT VSI approach, findability is still a bit difficult, right? There's either the data is local, it's on some private S3 bucket that Lynker runs. This URL is kind of difficult to find unless you knew this VRT file lived there. You may not know it existed. So findability is still a little bit of an issue, but access has become streamlined. Pass it in AOI, say this is the data I want, this is the data source. You get data exactly what you want. So there's no longer these artificial borders that come as part of the data set. Interoperability, again, is really good. Anything that uses GDAL, whether you're doing it at the command line, R or Python, you can hit that VRT file in the same way. And data is no longer duplicated or downloaded. And anything that happens at the USGS, that's the data that's hit, that's the data that's used. There's no longer private copies sitting on individuals' disks, and it stays up to date just by the nature of how the data is stored. I want to take a little bit of a detour because I think this is a pretty tech-savvy group that we showed an S3 example, a VSI curl example, and we really talked about gridded data as a whole. But it's worth noting that GDAL and OGR both respect these VSI prefix calls. So GDAL is the data or the software that gives you access to gridded data. OGR is one that typically gives you access to your vector data. Both of them are going to respect these VSI S3, VSI curl, VSI zip, VSI gzip. Any of the calls you might want to command or call. And most critically, they can be chained together. So we'll show one little example here that's kind of a detour again, but I want to make sure that this is brought to people's attention. NOAA maintains these AHAPS gauges, which gives flood forecast at location specific to river forecasting centers. And they give out this data as a shape file stored in the tar zip file. If you wanted immediate access to this and you didn't want to go download or build out your URL, you can chain a VSI curl to your zip file, untar it with VSI tar, and pull out the explicit shapefile name that you want within it. So there's some challenges here. You have to know the name of the file that you want that's within the zip file. But assuming there's a consistent pattern and consistent logic to how these are made, you can build out systems that no longer need to download data, but can actually stream it in real time. So one thing we've done with this is, as we're making flood maps for NOAA, we want to validate it against different systems that aren't necessarily hand-based. This single call run every hour will get us the latest 24-hour forecast because there's a consistent naming convention with it. And again, we never have to download it. We never have to store it. It reads almost instantly, and we have direct access because we've been able to chain tar commands with curl commands and knowing the format of the data. But again, before we get to the end, the challenge is you do have to know where this URL lives, and you have to know what's in the zip file, and that can sometimes be a bit of a challenge. There's also some complexities that arise with base implementation, so I don't want to give the false hope that this is going to be the magic bullet to anything and everything. Sometimes files don't follow conventions.
Can I ask a question?
Yeah.
Yeah, the prior one, you say, is it untarred into memory and then you go find that shapefile?
Yep, so it's just reading it directly. So I honestly couldn't tell you the magic about how the unzip's happening. That's all happening in the IO on the C code side. But it's able to read into that tar compression, pull out the specific one it wants, and then through VSI curl actually read just that shapefile. Because OGR knows how to deal with the shapefile, it finds all your projections and DBF files and everything with it.
But does it have to untar the entire TGZ archive in order to find that file?
That's more than I actually know, but I would imagine no, because this happens almost instantly.
All right.
Yeah, thanks. Yeah, so some base implementation. So NOAA is well known, I might say, for having netcdf files that don't necessarily match some conventions. This has caused some challenges that Dave and I have worked on for a while, but this particular example that I wanted to show here shows that base implementations alone aren't always enough. So this is one of those forecast files. So it's a National Water Model short range forecast that was made today. For CONUS, and it's the channel routing. So channel routing provides stream flow forecast. So it's not a gridded netcdf file. It's just vectors that are indexed to a COM ID or a feature ID. VSI curl wasn't enough to open this up. It wasn't able to fully understand what this is because something in the specification was missing. However, if we specify at the front of it that we know it's an HDF5 driver, not necessarily a netcdf, we still are able to read it. So we're saying the driver we want is HDF5. The path we want to read is this particular URL prefixed with the VSI curl. And the particular attribute we want out of the netcdf file, netcdf, unlike TIFF, you can have multiple different variables stored within there, is this stream flow. And so if you're able to chain together this URL, you can use GDAL. Again, we're using the R-based version of it, so GDAL implemented through Terra. We can pull out the values and actually get stream flow values for their particular feature IDs. So this is another way that we don't need to download this 23 megabyte file each time. We can have direct access to the particular array of data that we want. But again, just kind of pointing out, sometimes you need to help this along when files aren't set up exactly how you might want them. And so then that leads us to the final rant, and that there is so much data in the world, and so much of this data is useful, and it's really impactful and gives a lot of value to any type of workflow you might have. But finding it and developing these patterns is not necessarily easy, right? If everyone has to go through and find for themselves that this requires an HDF driver, and you need to prefix it with this colon and these two backslashes, things can get a little bit tough. And sometimes it would just be easier to download the files and continue in that way. And so that's what I would want to talk about is Rave 3, which is some of the flat data catalog work they've been working on with Dave, USGS, NOAA, and then back in grad school at UCSB as well. And we've started implementing some of this. It's by no means complete or finalized, but it has given us a lot of power. And we're calling these the Climate R catalogs. And as you can see at the top, the goal is to automate a collection of data catalogs that are usable with R. So again, any GDAL implementation, so Terra, GDAL.io, GeoKnife, Stars, or in Python. GDP tools that Rich McDonald is building also provides nice access to this catalog. They're built using targets, which is a make-like pipeline that keeps them up to date. And right now we're just storing them through GitHub.io. So you can access Parquet files, JSON files, RDS files. Any of them are stored in this catalog, depending on the extension you want. Eventually, we'll probably get them over into an S3 bucket. But for now, they're going to sit as they are. And the scope that we have for this is we want to be able to access aggregated netCDF files, non-aggregated netCDF files, any TIFF, COG, BRT that's hosted in S3, FTP, or any other source, and eventually stack catalogs, but that's currently a work in progress. So if we look at what this catalog has in it right now, has 107,000 data sets, has 28 columns and things describing these data sets, such as what is the ID, what is the actual asset of this information, where is the URL that it lives, what type of data does it have? So is it a BRT file, is it a COG file, is it an OpenDAP file? And then other information about the variables it stores, if it's climate data, what's the model and ensemble that it came from. And then critically, information about its time bounds, its X and Y bounds, its coordinate reference system, and how the data is packed. Probably out of scope for today, but we also talk about if it's tiled. So some data sets store information by different years or different forecast projections. So it may be tiled in time, or things like MODIS or Landsat have spatial tiling, which there's different data sets for different parts of the Earth, and you might want to tile them in X, Y, Y. When we return to that LC map example at the beginning, instead of having to build out that data dictionary ourselves or know that CU is the shortcut for CONUS, or that, LCPRI is actually the primary land cover for 1985, we can search this catalog directly for things that we want. So if we want land cover for 1985 from LC map, this catalog becomes easier to search. We're also able to say if we have AOIs, does it cover that area? And if we have particular time bounds, will it cover the time bounds that we're interested in? So there's just metadata about that information that can be built automatically through different GitHub actions and workflows. And what this ultimately allows us to do with what we've seen before is say, and this was actually a real example we had for NOAA, we wanted to build a new hydrologic formulation that required some sort of parameterization related to land cover, soil, and elevation, as well as topographic wetness index. So we said, we know there's LC map data in this catalog. We know there's Polaris soil data in this catalog. We know there's 3-depth data within this catalog. And for NOAA, we built out a CONUS TWI grid as well. We can build out those 4 URLs directly and say, hey, here's an area of interest that we want, and we have immediate access to those 4. And what's cool about this is LC map is hosted by USGS. Polaris is hosted by Duke. USGS 3-depth is hosted on the national map, and Lynker is hosting this TWI file. Doesn't matter where they are, what their resolution is, where their different domains are, because we know where the URLs are and they're findable in a consistent way, we're able to get immediate access to disparate data sets that help us answer a consistent pattern. And on the B side, we have some shortcuts as well that just kind of highlight the OpenDAP capabilities as well. It's beyond the scope of what we're talking about today, but you can grab things like precipitation for the state of Florida for a time bounds. Again, because the data is articulated in a consistent catalog, regardless of its native format or where it's living natively. We've done the same thing with the national water model data. So that was all for climate, land cover, land characteristic information. If you would believe it, the ways that NOAA has decided to host and archive national water model information, there are 599 different combinations. They're spread across different versions, different cloud environments, different Nomad servers, different different configurations, different output files. But by articulating them in this individual way, we can say things like get the latest forecast file from Nomads and pull out a time series. Or go to Google Cloud Compute, build a URL for 2020. So this is the forecast that was made on January 1st of 2020. Get one forecast hour forward and pull out your streamflow IDs as well. And the same kind of idea works for gridded data. Go find some gridded data on AWS for the LDAS outs. So that's the land surface outs, and pull out accumulated evapotranspiration. Again, data for Colorado for a particular variable is at your fingertips, regardless of what cloud environment it's in, regardless of its format, regardless of if it's weird, like in this particular product. US has been flipped because they packed it in the wrong way. The utilities in the catalog would tell us that the top to bottom is flipped, so it reads in the right way. But those can all be automated again. And they can provide ultimately much more complex workflows, such as pulling out elevation, water surface elevation data from a schism ocean model and interpolating it onto a land surface grid. Again, interpolate XYZ. It's a GDAL wrapper written in R, but it is hitting GDAL directly. But the key is this is a huge multi-gigabyte file. We just want a few things out of it, and we can access those series based off of the individual Nomad file list itself. So the key I want to make here is Nomad's file list is bringing in that information of what data is available. Get time series is using that catalog to say we know information from the National Water Model has to have that HDF5 driver appended to it. It has to take your variable names that you want and use that : / pattern. So it's taking out some of the complexity about how these different data sets are actually accessed, but the data is all exactly where it was output. We don't do any data archiving or data management ourselves. We're simply federating access patterns to it. And if we combine these three things, VRT catalogs, VSI access patterns, and flat data catalogs, all of a sudden findability becomes much easier. We know where the data is and it becomes searchable. Access is simple. We can give an area of interest and a time bounds that we want, and we get the data for that, regardless of whether it's tiled in an XY direction or tiled through time. It's interoperable. We'll show this in 1 second here. Because we're just passing GDAL interpretable path names and path patterns, it doesn't matter if you're using R or Python or the command line. Again, some of the things we've shown above in some of these slides, there are shortcuts written around it, but that doesn't mean they're limited to R in any way. And as far as data duplication, download, we are not downloading or redistributing any of this information. All 107,000 data sets that are indexed in that catalog live where the original creators put them. They're updated and maintained and formatted in the way that those original creators decide that they should be. We just have a pattern to access them that tells us exactly, what to expect when we go and look in that location. And then, as I said, we have been showing some R implementations through these examples, but Rich McDonald over at USGS WMA has made a really cool package called GDP Tools. It does a ton of things, but one of the examples I wanted to show is it is able to take advantage of this catalog for Python users as well. So the catalog itself is really what I hope is the takeaway from a lot of this, that you have particular patterns, you describe it in a similar way, all of a sudden your language of access doesn't really matter anymore. And the last thing, and then I'd like to part with some community thoughts that getting data online is awesome. None of this would be possible without the data creators or the data itself. The request would be to think about how you're formatting and organizing data for these remote access patterns. Things like large zip, 10 gig zip files like we were seeing with Oak Ridge can still be slow, can be hard to access, can be difficult to build out those patterns in a consistent way. There's really not a need for zip files anymore if you want to promote kind of remote-based access. Document your data in a way that is indexable and discoverable. All of those 107,000 data sets did this in a way that we can actually go and scrape out, what's their extent, what's their resolution, what's their bounds, what's their timeframes. Wouldn't be possible without that documentation in the data itself. And then lastly, if you're redistributing or reformatting data for a particular use case, and again, this is something Dave and I have done. We've done that with National Water Model data. It's really hard to access long time series and individual netcdf files. But we got to find a way to express that in the data description itself so that we know, what we're getting with different data sets that host the same raw data at the end of the day. And with that, I think, thank you. Yeah, if any of this type of work excites you, I'd be remiss if I didn't list that we are hiring kind of in this exact area: data accessibility, data use, landscape characterization. Would love to talk to you if that's something that interests you. And otherwise, hopefully, Dave, I was right on about 30 minutes and we can have some good discussion.
Yeah, it's fantastic. Thank you, Mike. I've watched this work unfold and emerge and just been super impressed. Your ability to hack GDAL URLs is unprecedented.
Thanks. Yeah.
So no, and really, I think that's my biggest takeaway here is like, there is so much stuff that's possible if you know the trick, if you know that backend kind of access pattern, and this flat catalog that kind of says here's how you get this specific variable is such an enabler. Like it's super cool. So I captured a collection of use cases and kind of high level notes in the minutes in here. And I guess the rest of the time here, I'd like to open the floor to questions and really what resources or what things do folks feel like should be recorded alongside this talk and just kind of captured for the future. And especially if they're, links and search terms and things that we could get out of Mike's head and get down onto some blog posts or wiki pages. I want to get at that kind of stuff. So.
Hey, Dave.
Yeah, go ahead, Ted.
Mike, that really nice talk. Amazing work. I agree with Dave. One question I had about that flat catalog is, what were the columns?
Yeah, so these 28 descriptors down the side here are what we found. I wouldn't call it the minimal set, but it's a minimal set of shortcuts needed to get the fastest access you can get to these different data sets. And so I'm happy to talk about any of these if there's some questions, but hopefully they're fairly self-descriptive.
But yeah, that's okay, so is this ID, what are you've got 107,000 rows.
Mm-hmm.
And are these the 28 different columns?
Yeah. Yes. Yeah.
Okay.
So these are the 28 columns. And then the rows they're just spread across this way. So row 1 has mock a day, row 2 has mock a day. You can see there's different assets within each of those. So there's 2,600 individual data providers. The ID is generally the data provider.
Okay. Great. Thanks.
Yeah.
Yeah, it's somewhere between variable metadata and data access cache metadata.
Yeah.
And I'm sorry if you said this and I missed it. Is the data here being eventually like manually collected? Like, is this data sets that you have found yourself?
Yeah, so where this project started, I went through and manually populated these, and we had, maybe 12 instead of 107,000. These are now all automated, but finding that root URL generally comes from, I knew which ones we were using for NOAA or for grad student work. And now they've been based off requests. So if a group comes and says, hey, we really need this particular data, and they can point to somewhere where it's hosted, it's pretty easy to add them at this point.
Yeah, it would be like, if we had infinite resources, this would be a fantastic thing for producers to just be like, if there was some web-based catalog rather than this being people having to actively request it. If when data is being produced, people were able to contribute to something that was web-based rather than having it be, someone who knows that your project exists and knows that that data exists, connects the two.
Yeah, that's I 100% agree, and that's kind of the sneaky. That's not sneaky. It's the motivation for looking at these stack catalogs. I think this is the community standard. It's what a lot of people are rallying around. They store a lot of information in deep nests that aren't necessarily access focused. They're really focused on describing the data. So there's things like data provenance, versioning, things you don't need explicitly just to speed up access of the data, but there are nice ways to unfold stack catalogs into this flat catalog. I think that might be a way to get at what you're hinting at, but there's a lot of work to go on that.
We got a question in the Google Doc about examples, kind of where people that haven't worked with this kind of thing before would start for some copy paste type examples just to get started. I don't know if Mike, if you want to speak to kind of where you learned some of this stuff, or how you got started shaping this flat catalog? Because, and there's an awful lot of knowledge and experience wrapped up in how that catalog is created.
Yeah, good places to start. It's a little tricky. The GDAL documentation is really great, but it's kind of limited. Here's your options, and go use them as you might. I think in this climate art catalogs, there's a targets file that has how we've actually built it out for each of these individual data sets. So that provides some of that, but it is R based. Most of what finding it was just finding data sets that we wanted access to and trying to find where they live natively, and then trying to chain these different commands together to get it to play nicely. There aren't at this point any like nice recipes or anything like that that you can kind of copy and paste to play with that I'm aware of.
Yeah, that you've encoded those recipes into your targets workflow, right?
Yes, yeah, but I'll be the first to admit it's in the way I interpret it, which probably is not the best way for someone trying to learn it. If that makes sense. Yeah.
It's kind of, you got to know it's possible, and then you got to go smash your head into a wall for a while and figure out how to do it. Unfortunately.
And I would say like 90% of the data out there plays nicely right off the bat. It's typically NOAA data that doesn't play nicely, and that's probably why I've been able to pick this all up, because that's the data I work with. But if you really want to struggle, play with NOAA data. Otherwise, go play with USGS data, and you'll pick it.
If you had to work with anybody else's enterprise legacy data, you'd have exactly the same issues. You're just sitting where you sit, so that's your experience.
That could be, yeah. That's the national water model stuff. I mean, even nomads. That's the brain buster.
Any other questions, or like what?
I've got a general question.
Yeah, go ahead.
Thanks. Thanks a lot for the presentation. Really interesting. What would be an obstacle for implementing this for like a data release or data stored on Sciencebase or a LPDAC? Because a lot of data, the first step is authentication, and after that, you can access the data.
Yeah. So on the authentication side, and Dave, you've worked with this a little bit. As long as like in R, again, that's where I'm familiar. S3 buckets or Sciencebase, as long as you authenticate your session, this all just kind of works. So as long as if you're working with AWS, just load your key and access secret into your environment, and all of these will work. And they actually give you pretty nice errors if you're not authenticated. One that we've had to work with in that data catalog, we have a lot of NASA data that requires a netrc and a DOS SRC file for your Earth Engine login. You can cache that. So we've written some things into that package that will request your login, keep it local. So we could play more with that, but I think it's annoying, but it's workable in every case I've seen so far. And Dave, you did Sciencebase authentication, right? You might be able to speak to that.
Yeah, I mean, for Sciencebase, it's a little more nuanced. They don't necessarily support that. Like the S3 and the Earth login integrates with curl, curl or Boto, depending which client you're using. For things like Sciencebase, if you're not putting things on public S3, it's going to be a little harder. I would imagine like HydroShare would be another example of a system that a project might have data stored behind authentication. That's a custom authentication that requires some kind of token at the API level. That's going to be a challenge. So But it's good to, it's good to remember we do have solutions for the big one, kind of the NASA Earth login, as well as more general S3, authenticated S3 access. So.
Great, thank you.
I had a question too. This is Quinn. I work at the National Geospatial Technical Operations Center for USGS. And I was just wondering about, to what degree does findability depend on human to human communication? So like if you were using a VRT hosted by one of these data producers, but the URL of that changed, does it really just boil down to someone needs to tell you, here's the new URL in order for this all to keep working? Or are there any kind of automated means for maintaining that findability?
Yeah, so I can speak to the national map case, and some of them are just going to be somebody's got to tell you. But right now, what those targets do is they'll run through each example. And so I think we have it set up to run every other week. It'll run through them, and if something errors out, it kind of kicks that data set out of the catalog, and we can go manually investigate, which I think is what you're hinting at. For some of them that are clear hierarchies in the data structure, we can actually go find it. So 3dep is one of those that if we can't find the VRT where we expect it, we actually just read the lines off the HTML page or the S3 bucket, look for VRT. If it exists, we try that one. Otherwise, we error out. So there are some hacks you can have in there, but that's still manual intervention at some level that has to be written. But once it's written, it can kind of carry on its own. Does that answer your question?
Yeah, that does. Thank you.
Yeah, the kind of stable entry point to a changing collection. I think you were alluding to that as well with forecast models where the file names change, but at least they show up in the same place every day. You can automate some of that, but if the location that those files land changes, somebody's going to have to make an adjustment to the configuration.
Yeah, and to that point, I guess that's actually an example here. So Git GCP, this actually knows the URLs because they don't change what's available. We know what's on Google Cloud Compute. We know the time ranges, and we know the pattern that URL should look like. Nomads is that one that updates every 48 hours and actually starts ditching data. So where this just generates patterns based off blue strings, this one goes and says, we know the main entry point, and we're going to read lines off that HTML page and see what's available. And once we read those, then we'll be able to determine what's your most current forecast. So there are ways around that, but this is a catalog approach that I would call language agnostic. I mean, somebody would have to write the very minimal Python implementation if they wanted Python. This has a lot of code logic in it to get to, because that's constantly updating.
Yeah, and I can see this kind of being the intersection with kind of the stack level data set catalog metadata, that given a stable entry point to a data set, you might have something that could go and build this catalog, and you'd have that kind of layer of logic that knew how to interpret the contents and build the catalog, but it would rely on that stable entry point.
Yeah.
So I've been capturing a few kind of questions and responses here in the takeaways. I guess are there major things people are hearing here that are worth carrying forward? The question about security is a really good one. That's actually I've been thinking about doing a future rant and rave on security and authentication for earth science data, because there's so many different, it seems like there's so many different approaches, but I think there's actually just a couple core patterns that would be worth us all kind of thinking about. Also want to get Evan Ralt to come in and actually tell us how all this works. Well, I will, I don't need to belabor if we're out of questions and there's no more specific things. I guess we got a hand up, Mike.
Oh, sorry, that's the clap reaction.
Oh, that's the clap hand. Nice. All right. Well, let's call it a day and take a little break before the next call. I will make sure that the notes and minutes and stuff that we took here today get transferred into the YouTube recording and into our future wiki content for this stuff. Thank you so much for stepping in and doing this talk on somewhat short notice, Mike.
Yeah.
And yeah, and I guess if folks have questions, feel free to hit any of us up on the ESIP Slack. That's kind of the place a lot of us have been meeting up and collaborating across various agencies and teams. Be more than happy to take some of this conversation to that venue, and yeah, we'll be in touch. Hopefully we'll see folks next month, where we will hear about open source geospatial in the from Tom Kurlitis, thinking about the Python ecosystem. So with that, take care, everybody, and have a good evening.
Thanks, Dave.
Cool.